Okay, so in the previous class we talked about the joint interpolated trajectories, right? And we kind of discussed that there are a number of ways where we can design the trajectory for our robot arm. And namely, there are this what we call the 4-3-4 trajectory, 3-5-3 trajectory, 5 cubic trajectory, and so on. So when we say 4-3-4 trajectory, we mean that this segment here, this will have a fourth order or fourth degree polynomial, and this midsection here we would have the third order polynomial, and finally the last section here we have the fourth order polynomial. Okay, so in our course we will only focus on 4-3-4 trajectory, because I don't see a point in learning other trajectories, because this is highly mathematical. I mean, you just have to substitute the values and compute the trajectories. So if you know 4-3-4, for sure you would know 3-5-3 and 5 cubic trajectories as well. Okay, so before we begin, let's recap that our trajectory for every joint would look like this. Okay, so it says here joint I. That means if you use sixth degree of freedom robot arm, then you would have 6 graphs as this. That means 1 for every joint. Okay, so let's talk about the x-axis first. So this is the time axis. So tau 0 is the real time at initial position. This is real time at lift off position. This is real time at set down position, and this is the real time at final position. So real time here means the actual time, right? For example, tau 0 can be 0. That means at time 0 you want your joint number 1, for example, have a certain value. So this is our initial position, right? Theta 0, and this can be 1 second, can be 2 seconds, can be 3 seconds. It depends on the motors and on the problem that you are solving. And we have a number of other constraints. The initial velocity and initial acceleration. That means at this point, when you start moving or actuating your joints, what is the initial velocity and initial acceleration? So if you imagine that you are doing this for a pick and place operation, so when you are picking an object, at that time, of course, most probably the velocity and acceleration will be 0, right? But that's not always the case. So it's like case by case basis. So usually in a question, if the values of initial velocity and initial acceleration are not given, that means it's 0. You assume it to be 0. That means you start from a static point, right? And similarly, we have final velocity and final acceleration at this point. So what is the acceleration and velocity at this point when you are placing an object, right? And again, usually it's 0, but not necessarily. Okay, in the actual application, for various reasons, you may have non-zero velocity and acceleration values. But once again, for a simple pick and place operation, the final velocity and acceleration values are zeros as well. All right? So please interrupt me anytime if you have questions, and don't forget to scan your attendance. Okay, I can see only 19 of you have scanned. All right, so this is what I meant when I said it's mathematical, right? You see, this is the equation for H1. This is the first trajectory segment. That means this is the equation for this segment right here. All right, this is H1. You don't have to memorize these equations. This will be given in your test and in your final exam. So later we will try to compute this, and it may seem a bit daunting, right? Because the equations are long, but as you will see later, because our initial acceleration velocity and final acceleration velocities are 0, you can cancel out many of these terms, and you can do this computation quite fast. Okay, so don't worry. So this is H1. This is H2, right? Where is H2? This is H2, second segment right here. And then finally, of course, we have H3. So in this chapter, it's all about computing these segments, right? So H1, H2, and H3 are designed or derived such that these points are passed through, right? That means from here, so H1 will make sure that the end point will go through theta 1, and H2 is derived such that it begins at theta 1, and so on. So these 4 points has to be covered by H1, H2, H3. All right, and then the point, and at this knot points we call it, right, theta 0, theta 1, theta 2, theta f. The segments are derived such that the whole trajectory is continuous and smooth. All right. So once again, this is initial position, set, lift off position, set down position, and the final position. All right, so if you recall, the lift-off position is the position where the end effector is away from the surface, right? In a normal direction, in a perpendicular direction. And similarly, theta 2, or the set-down position, is where the end effector is perpendicular away from your final position. Okay, so if you cannot remember, let me quickly run the simulation and show you. Oops. Okay, so this is the initial pose, the red one, right? X0, Y0, Z0, initial pose. It goes straight up to lift off pose, and this is the set down pose, and finally the final pose. Okay, I say pose because I'm referring to the coordinate frame. So this is the pose of the end effector. So you have 4 poses of the end effector that we have to obey when we design our trajectory. So from these poses, we can do inverse kinematics to get the initial position, lift off position, set down position, and the final position. All right. Back to the slides. So it'll be easier just to look at an example for better understanding, right? So this is example 1 in this chapter. A Puma 560 robot is used to pick and place an object. So the moment I say pick and place, you should assume that the initial and final velocities and accelerations are 0. Okay. The required pick and place and effector positions and orientations, or the pose, right? From chapter 2, remember, position and orientations are also known as pose, are given by homogeneous transformation matrices T0 and Tf respectively. So this is the initial pose. This is the final pose of the end effector. And we have shown this in 4 figures in various angles, right, or view angles. So this is the initial pose. That means when you pick, so you can imagine this is where your n effector picks the object, right? An object. So this is the initial pose. So what does it mean is that the z here should be aligned with z0. Y of the n effector should be aligned with y0. So it picks, but it should not go directly to the final pose. It should go to the lift off pose and then to the set down pose, only then to the final pose. So this is how the end effector will be, right? The position orientation of it when it places the object. So this is pick pose, this is the place pose, but we call this the initial pose and the final pose. This is the top view, if it matters to you, right? And this is the side view, and this is the other side view. Okay, so we can see it picks from slightly higher compared to the place position, right? Doesn't matter. Anyway, the question continues, right? From inverse kinematics, these are the angles that we obtain using arm to be -1. If you remember, -1 should be left, right? Left arm. Elbow 1, that means this is elbow above. Okay, we get this, and the final positions are this. So you might be wondering why we have 6 values here, because this is for theta 1 or joint number 1. This is joint 2, joint 3, joint 4, joint 5, joint 6. And 0 here refers to these are the initial configuration, right? Initial configuration of the robot arm. And similarly, the final position, again, we have 6 as well, 6 values, 1 for every joint. So this do not include the lift off and the set down positions. In the question, you are given the values of lift off and set down positions. So it says design a 434 trajectory for joint 1 with lift off position theta 1, 1. So the first subscript 1, it refers to because this is the lift off position. So let me go back a few slides. So theta 0, theta 1, theta 2, theta f. Okay. So the first subscript refers to theta 1, which is the lift off. And here the first subscript refers to set down. Second subscript refers to the joint, because we are interested in joint number 1. Of course, in reality, you have to do this. You have to design 434 trajectories for joint number 1 up to joint number 6. Okay, but this is an exercise that you have to compute. We only consider one joint. And we also given the real time, right? This is the real time at initial position, real time at lift off position, real time at set down position, and real time at final position, 0, 1, 2, 3. And these are the answers. Okay, so you can try this, but we will try this shortly. So before we proceed, I will try to explain the question further for better understanding. Meanwhile, you have any question? No? Okay. Oh, someone emailed me already. Gun. That was fast. Gun. Okay, I'll reply after class. All right, for your test paper. Okay. I will try to explain the question further. Right. So for that, I need to copy this figure. So it's a bit too small. I hope you can see. All right. So this is, what is this? This is the initial pose, right? Initial pose, position and orientation of the n effector that we desire. And this is the final pose. Final pose of our n effector. Okay. So from here, right? From here, using inverse kinematics chapter, the previous chapter, chapter 4, using inverse kinematics, we will obtain or maybe this is the wrong way of writing. Let me correct this quickly. So from here, using inverse kinematics, we will obtain theta 0. So theta 0 here refers to initial position. This is initial position vector. And it would have 6 elements, right? Because we have 6 joints. So we have theta 0, theta 0, 1, theta 0, 2, and so on, up to theta 0, 6 transpose. And this is exactly given in the question. In reality, you have to compute this. This one, right? So 2.1438 and so on. Should I write it? Okay, let's just write it quickly. Okay. So what it means is that, so when the end effector of the robot arm is aligned with the initial pose, theta 1, the first joint will be 2.1438 radians, and so on. Okay. So similarly, we should do the same for the final pose. So from here, using inverse kinematics, we can obtain the configuration of the robot arm, which means the joint angles, right, the angles of every joint at final pose. And of course, because it's final position, we call it theta f. It has 6 elements because this is a 6-degree robot arm. So we have theta f1, theta f2, and from the slides, this is this one. Okay. All right. So are we done? We are not done yet, right? Because this is the initial pose, we have the final pose. We need 2 more poses. We need the lift off pose and the set down pose. So even though in the question it did not ask you to compute, but in reality, in actual application, you have to compute it, right? So where is this lift off pose, or how does it look like, right? It is directly above, right? It's in parallel, normal to the initial pose. Should be somewhere around here. Okay. And I'm sorry, I have to draw it small. Okay, let me draw it. It can be anywhere along this line, all right? So normally it wouldn't be this long, but because I have space constraint, that's why I'm drawing it here. So it might look something like this. It is parallel. That means y0 is parallel with y1. Z1 is parallel with Z1, and X1 should be in parallel with X0. But the position is away from the initial pose, right? And it's a normal, right? It's normal, which means it's away in parallel. Okay. So again, we have to do inverse kinematics for this. Do inverse kinematics, and you would get theta 1. So theta 1 1, theta 1 2, theta 1 3, theta 1 6, and this is what we call the lift off position. Right? And don't forget the set down position. So set down position should be in normal, away from the final pose. So you might have your Z0, Z2 to be that way. This is where's X? So this is your X, X2. That is your Y2. Okay, I hope you can see. If you cannot see, I can draw it bigger if you want. So from here, again, inverse kinematics. you would have theta 2. So theta to 1, theta to 2, up to theta to 6. So in the question in our slides, it says that we have to consider joint 1, right? So because we consider joint 1, you only have to take note of this first point, this one, and this one. All right, and this has been computed for you. Theta 1, 1 is given in the question, right? 2.1438. Theta 2, 1 is minus 0.2777. Okay, and the question says we have to design the trajectory for theta 1. So this should be the graph for theta 1, the first joint. Let me see if I can draw it straight. Yes, I cannot. Where is my toolbar? All right. So we have to design a trajectory for joint number 1. So this is where we have our theta 0, 1. So this should be theta 1, 1. The final one should be theta f1, and this is theta 2, 1. Alright, initial position for joint number 1, lift off position for joint number 1, set down position for joint number 1, final position for joint number 1. And we have to make sure it obeys, of course, it obeys the time constraint, right? This should be tau 0, this is tau 1, and here should be tau 2, and this should be tau f, and this is the time in seconds. This is in radians. Okay, so now we have to compute this. We have to compute the 3 segments. What are the 3 segments? This is h1 of t, this is h2 of t, and this is h3 of t. And these equations are given in the notes. These are the equations, right? So let's try to compute this now. If you have no further questions, I'll proceed with computing these equations. Can you please prepare your calculator so that you can help me to compute? Please bring out your calculators. So if you look at H1, right, the first thing that we have to compute is we have to compute all this: delta 1, delta 2, delta f, T1, T2, Tf. Okay, so for that we need some information. We need theta 0, theta 1, theta 2, and so on. Okay, so from the question we can see that theta 0 is given by this, right? 2.1438. Theta, so this is theta 0, 1, theta 1, 1. Well, because we are considering joint number 1, you can kind of ignore the second subscript, maybe for simplicity, right? So I'm just calling theta 0 and theta 1. But at the back of your mind, you know that we are referring to joint number 1. So what is theta 1? It's 2.1438. It's the same. Then theta 2 is this one, right? Minus. Okay. Theta f is given by this, right? All right. What is tau 0? Tau 0 is 0. It's given here. Tau 1 is 1. Tau 2 is 2. And tau f is 3. Okay. So referring to the formula, I'm going to slide number 10. We have to compute T1, right? T1 is, if you see T1 is tau 1 minus tau 0. T2 is tau 2 minus tau 1. And Tf is tau f minus tau 2. So they all equal to each other, right? So T1 equals to T, in this particular example, T1 equals to T2 equals to Tf equals to 1. Okay? Because 1 minus 0 is 1, 2 minus 1 is 1, 3 minus 2 is 1. Alright, what is delta 1? Delta 1 is theta 1 minus theta 0. Right? Theta 1 minus theta 0 is 0. Right? You don't have to use your calculator. Theta 2 is theta 2 minus theta 1. Theta 2 minus theta 1. Okay. Can you please compute it for me? And maybe write it down, the answer, or you can speak up. Okay? Wow, so fast. Alright. Minus 2.4215. Okay, good, thank you. How about theta f? Theta f is this one minus this one, right? 0.044. Alright, good. That's good. Next, we are ready to compute G, right? Let me use another ink, another color. G is Tf over T2. Tf is 1, T2 is 1, so 1 over 1 plus 2Tf over T1 plus 2 plus 3t2 over t1. What is this? 1 plus 2, 3 plus 2, 5 plus 3, 8. Okay, that was simple, right? Let's move back to slide number 9. Okay, F is getting a bit crazier, alright? It's okay, but don't worry. What is F? F is 2 delta 1. Delta 1 is 0, right? We are lucky because it happens to be 0, not necessarily, alright? So in this particular example, delta 1 is 0. So you can how to say, disregard. You can what's the word? I'm running out of words. You can forget about this whole term, right? You can cancel out this whole term because 2 multiplies 0, multiply the whole thing is 0. Okay. Then this one you have to compute. So minus delta 2, we have this minus is positive, right? 2.4215. T1 is 1, T2 is 1. Okay, just leave it as it is. Plus 3 plus TF is 1, T2 is 1, plus 1. Plus 2 multiply delta F, 0.044, right? Minus V0. What is V0, guys? Because in the question, it does not say, right, what is V0. And it also says we are doing this for pick and place. So it is very safe to assume that V0 is 0. So the whole thing can be cancelled out. Vf, the final velocity, is also 0. The initial acceleration is 0. Final acceleration is 0. So everything is 0. Okay, now what is F? Can you please compute for me? Wow, that was fast. 9.774. Thank you, Chia Ching Seng. What is sigma? F over G. What is sigma? .2218. Thank you again, Chia Ching Seng. 2218. Okay, I need to copy this formula because I'm running out of space. Alright, so delta 1 is 0, 0 minus 0 minus 0 minus 1.2218, t to the power of 4. Okay, remember H1 is, so we are doing 434 trajectory, right? So the highest, so the H1 is 4th degree polynomial. So that's why t to the power of 4 plus sigma, again, 1.2218 t cube plus A0 is 0, right? V0 is 0 plus theta 0. What is theta 0? 2.1438. 2.1438. Okay, let's check. So minus 1.2218 t4 plus 1.2218 t to the power of 3 plus 2.1438. So that's correct. H1 is correct. Okay. Do I want to show H2 and H3? Okay, guys, do you want me to show H2 and H3? Because it's simple, right? Or would you like to compute yourself? Jerry says, no need, sir. Thank you, Jerry. Very kind of you. How about anyone else? No need, can compute. Yeah, very good. Because it's very simple. This is just arithmetic, right? Just substitute and compute. Okay, guys. So that's about it for today then. I will try to prepare some tutorial questions. I will try. I'm going to. The plan is I want to prepare. I want let you try this simulation so that you will have a better understanding. So I will try to formulate this in a tutorial exercise. Okay, so that you can do it yourself. So there's another exercise. Again, it's the same. So this is one exercise, and the other. So once you get that right, the next thing is to visualize how does it look like. So this, I think I plotted this using MATLAB. So it's accurate. So as you can see, it does not really look like the ideal trajectory that we desire, right? Because we have a slight overshoot and slight undershoot and so on. So remember, this is our, let me make it bigger. This is tau 0, right? The time at initial position. So this is initial position. Initial position is 2.1438. So here, right? 2.1438. So this is tau 1, the time at lift-off position. If you notice, it happens to be the same. There's a reason why it's the same, but there's not a reason why. It's not wrong to have the same, and I hope you can figure that out yourself. If we don't understand why theta 0 and theta 1 are the same, please ask me in the next class. I would be glad to explain to you. So this is theta 2. Sorry, this is tau 2, time at set down position. Right? What is set down position? Minus 0.2777. And then this is tau 3. This is the time or real time at final position. Again, you might ask me, right? How come the set down position or angle is less than the final position? So please think about that, okay? Because maybe you expected, right? I don't know, maybe you expected the graph to be exactly like this, which means theta 1 is bigger than theta 0, and maybe theta f is higher or bigger than theta 2. That's what you expected. But when we computed using the mathematics, we got a graph that looks like this. Okay. The short answer to that is that it doesn't matter how does it look like, right? Because at the end of the day, what matters is the trajectory of the robot. See, the desired trajectory is correct. I mean, the trajectory is as we desire is correct, you see. So it doesn't matter how each joint individually behave. What matters is that it does begin from initial pose, it goes to the lift off pose, it goes to the set down pose, and then to the final pose correctly. That's what matters to us. All right. Okay. So next in the slides we have, where's my So there's another exercise on slide 21. It's similar, right? Exactly the same, but except that the initial and final poses are different. The procedure is the same. Again, you have to compute H1, H2, H3, and so on. All right, nothing much here. So that's all for today. Before Thursday, I will try to prepare the tutorial question for you to try. And until Thursday, if you have time, if you don't have time, it's okay. If you have time, please try to compute or to solve these two examples. All right. Example on slide 13 and slide 21. All right. Do you have any question? If you don't have any question, that's all for today. And please email me by today, okay? Section 1 only. Email me by today. I will reply with your test paper. If you email me tomorrow, I will take a few days to reply. But if you email me today, I will reply today itself. Please tell your friends, Section 1, email me today to receive your test paper. And if you have any question about the marks, please contact me by email today. All right. So that's all for today, everyone. Thank you very much for your attention. I will upload this video on e-learning. Have a nice day.
Thank you, sir.
Thank you.
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 Thank you, sir.
Thank you.